Friction and force normal. Friction is what keeps these cars from sliding down the hill. Friction is the resistance to movement and is always directed in the opposite direction of that movement. For example, if you are pushing on an object, friction will be pointing in the opposite direction. Friction depends on the force pressing the surfaces together and the types of surfaces in contact. For example, if two surfaces are pressed together more forcefully, there will be more friction. And if the two surfaces are rougher, then there will be more friction. Friction does not depend on the surface area in contact or the speed in which they interact. Think about it. Why does putting sandbags in your truck help you to not slide on the ice? It's because you're increasing the force pressing these surfaces together. By putting sandbags in your truck, you are loading up the back of your truck with more force, meaning that there is more of a push that's bringing together the tire and the road. So that's increasing the friction, helping you not slide on the ice. There are three types of friction: static friction, which opposes the start of a movement; kinetic friction, which opposes an object already in motion; and rolling friction, which opposes an object rolling without slipping. We're not really going to talk about rolling friction that much. That's the friction, for example, if you have a car and the car's wheels are spinning as it moves, there's friction in between the tires and the earth, and that's an example of rolling friction. We're going to focus more on static and kinetic friction. Static friction is opposing the start of a movement, and it's the largest type of friction because it has to overcome inertia. Think about it. If you have an object at rest, like a giant shelf, and you're pushing it and you're trying to get it to move, this shelf is an object at rest. And in order to get it to move, you have to overcome its inertia and desire to be at rest and push it so that it will begin that motion. And that's called overcoming its static friction. And you can see that in this graph of the motion, that as you push, this is the static region. And you can see at this point right here at the top is where the object will start to move. After it has hit this static friction, you can see that the graph then decreases significantly. An idealistic graph, instead of looking like this, might look something more like this. You can see that there's a sudden drop in this area, and then a smaller amount of friction. And that's kinetic or sliding friction. That's opposing an object already in motion. And you can see that it's less. You might consider the static friction to be like the activation energy needed to get something to start moving. And that this extra amount right here is the amount of energy that you have to put in to get it to start moving, such as the activation energy in chemistry. What's weird about friction is that since this initial part of the graph is a straight line, that's implying that as you push with a certain amount, it'll resist with only that certain amount until you hit this maximum threshold of friction that you have to overcome. Let's say, for example, that it takes 100 newtons of force to overcome the friction of an object. What that means is that as you start pushing, let's say this person is starting pushing. Let's say if this person is pushing with a force of 20, that the friction acting back on her is only going to be 20. It's not like you're pushing forward with 20 and the force backwards was 100. If that was the case, the friction would cause the object to accelerate backwards, which is ridiculous. No, what happens is that as you push with 20, it's resisting with 20. And as you push, for example, with 40, it's going to resist with 40. And as you push at 100, or it's going to resist with exactly 100. And at that point, it's going to become an object that's moving at a constant rate. Because as you push at 100, and it's resisting back at 100, remember that this image can show something either at rest or moving at a constant velocity. And you can see right here at this moment, it's going to start moving at a constant velocity. And then suddenly, once it starts moving, it's going to only require 80 newtons of force to continue pushing. And that's what's happening in its kinetic region, right? You can see here, this person is trying to push, but their force applied is less than the force friction. So this object is not moving. But once you have a person helping, you can see that your force applied is going to be equal to the force friction. And this is where it starts to move at a constant velocity. And now that it has started moving, you can see that the force applied is going to be larger than the force friction of the kinetic friction once it's already in motion. So you can see that's going to cause it to accelerate forwards. Air resistance is a frictionless force that affects objects moving through the air. It depends on an object's size, shape, and speed. So air resistance is the reason why a feather and a hammer might appear to fall at different rates in real life. But on the moon, when there's no air resistance, they'll fall at the same rate. The air resistance that the feather exhibits in real life is due to its size, shape, and speed. This picture right here shows an elephant falling and a feather falling, and showing that they're accelerating theoretically at the same rate in a vacuum. But that in real life, their size, shape, and speed might affect the rate at which they fall. Terminal velocity is a special word that is the point where a falling object stops accelerating. It's still falling. It's just not accelerating as it falls. So it's at a constant velocity. So this happens when air resistance and gravity are equal and opposite. You can see in this graph that as an object falls, that its initial acceleration or slope of the line might be negative 9.8. And that as it continues to fall, the acceleration is going to approach 0. And not mean that it's not falling, just meaning that it is falling but not accelerating as it does. And this happens due to air resistance. This terminal velociraptor over here has equal and opposite force air and force gravity. So he's falling at his terminal velociraptoriness. The coefficient of friction is represented by the Greek letter mu. The coefficient of friction is defined by each pair of surfaces, and the coefficients for static and kinetic friction are different. You'll notice in this graph that the static friction is always larger than the kinetic friction. And once again, that's because in static friction, you have to overcome the inertia of a stopped object. Here's your equation for force of friction. Force of friction is going to equal the coefficient of friction times the force normal. So this is showing us that, as we learned before, that friction is defined by the force pushing two surfaces together and the type of surface. So these right here are the two components for calculating our force of friction. If you look at this chart over here on the right, you can see that the coefficient of friction varies wildly between two surfaces. You can see that rubber on concrete, for example, has a very significant coefficient of friction than rubber on wet concrete, which is why it's much harder to stop your car in the rain. You can see that Teflon, for example, has a very low coefficient of friction, which is why your eggs don't stick to it. And that synovial joints in humans, such as your arms or your legs or your shoulder joints, have an incredibly low coefficient of friction. And that's why every time your body moves, your bones aren't rubbing against each other. Let's do some sample calculations using a coefficient of friction. What force is needed to move 12 kilograms of rubber at a constant velocity across dry concrete? Since it's moving at a constant velocity, that means that the force applied has to equal the force friction. I've just filled in the force gravity and the force normal, which I calculated by doing force equals mass times acceleration. So I did 12 times 9.8, and that gave me the value for the force gravity, which is equal and opposite to my force normal. Since it's moving at a constant velocity, that means that whatever force we're applying has to equal our force friction backwards. Let's calculate our force friction. Force friction equals mu times force normal. So the force normal we have just found to be 117.6. And our coefficient of friction, let's look it up. Rubber across dry concrete, right here. So since it is needed to move, we have to ask ourselves if we're measuring the static or kinetic friction. And I'm going to choose the kinetic friction because I assume that by saying move, it means continue to move or keep moving. So I'm going to fill in my coefficient of friction, 0.8 times my force normal, 117.6, and I'm going to get a force friction of 94.1 newtons. So that means that the force applied needed to move it would also be 94.1 newtons. There we go. Let's try another example. What is the force needed to slide a stationary 150 kilogram rubber block across wet concrete? I'm going to start off with a free body diagram. And I'm going to fill in some values. First, by finding my force gravity by multiplying 150 times 9.8. which gives us 1,470 as force gravity and force normal. Next, let's find our force friction by saying force friction is mu times force normal. Our mu right here is going to be between rubber and wet concrete. It's the kinetic friction because the object is already in motion. So I'm going to multiply, 0.25 times our force normal, which gives us a total friction of 367.5. Our last example. Determine the acceleration of a sliding 8.5 kilogram block if a force of 72 newtons is applied to it. Up at the top, you can see the force applied of 72 newtons, our unknown force friction, as well as a force gravity and a force normal of 83.3 newtons. So in order to find the acceleration, I'd like to find the net force. And in order to do that, I need to find the force friction. So since it's already sliding, I'll do the kinetic friction times our force normal, which gives us a force friction of 40 newtons. That means that if we were to look at this in a similar way that we've done our others, with this chart that says the mass, the acceleration, and the net force, we know that our force gravity and our force normal are equal and opposite, which means that our net force has to be left and right. Which I'm calculating to be 32 newtons to the right by doing 72 minus 40. All we have to do now is calculate the acceleration. Knowing that net force equals mass times acceleration, we can say 32 equals 8.5a, and that a would therefore equal 3.8 meters per second squared. Nice work.